few scenes from that great old MGM movie, Boomtown, with Clark Gable and Spencer Tracy. Well, that's not the way oil was usually found. In fact, those Boomtown derricks, and especially that rather suspicious-looking pool and clouds, were made or painted on a sound stage on the back lot over at the studio a couple of miles from here. We all know about Hollywood, but we still don't know much about how people really find oil. A lot of myths connected with those fabulous Texas, Oklahoma, and California fields. A lot of truth, too. Now, some guys did get real lucky. A strike on the last try, 10 in a row, that sort of thing. Yeah, it often seemed like magic to them and to us. But the vast majority of wildcatters went bust on dry holes. It was an adventure that ranked with the gold rush, empire builders, and nobodies. But what they did remade our world, put it on wheels.
A good man can sniff it. He can smell it, even if it's 300 feet down.
What if you lose it all?
Hell, that's a game. Win a few, lose a few. Look at Marland Oil.
No one in the world knows the oil business better than I do. I was a pioneer in geology and petroleum engineering. I've discovered more oil fields than any other man in the world. I know the way back to another fortune.
E.W. Marlin was wrong. Oil was getting harder and harder to find. He knew some science, but not enough. And he never found another drop. All the easy oil has been found. Since the early 1940s, an array of scientific and engineering disciplines led by the exploration geophysicists has been engaged in a massive global effort to find the rest. Oil has become increasingly difficult and costly to find, but it is here. Geophysicists and other earth scientists have proved it with sophisticated tools, with daring and original methods, with scientific principles. They have seen untold deposits of oil beneath the most remote and hostile reaches of this planet. Here they have found the source of lubricants and plastics, pesticides and herbicides, synthetics, pharmaceuticals and fertilizers from here, paints and inks, tires and tile, film here, and countless billions of barrels of crude to warm and cool us, and to run the machines that run the world. And yet, with all of our dependence on oil and gas, it is not a renewable resource. As precious as it is, there is an end to it.
We call our science geophysical prospecting. And in that sense, we are prospectors, much like the prospectors of past times. Indeed, much of what it takes to be a prospector today is what it took in Dawson City in gold rush days. Geophysics and the fate of nations. Does that sound pretentious? Well, take Britain. Not so many years ago, in deep financial trouble. Today, poised for a major resurgence. And how did it happen? The North Sea. Pure and simply the North Sea. The gas first, and then the oil. Today, Britain is the only major industrial country in the West which is self-sufficient in energy.
The rock formations here in Scotland are the same age as those across the North Sea in Norway. Ancient rocks, no hope at all of finding oil, or so most experts thought. Yet out there, beneath the sea, lay a vast basin of younger rocks. Source rocks, reservoir rocks, cap rocks, everything it takes to generate and trap oil. Many skills were involved in this major discovery. Geology, marine engineering, even just plain old seamanship. But the indispensable skill was geophysics.
How do you read and analyze what cannot be seen? Is there a signature, a scientific code to indicate that a possible oil or gas-bearing structure exists 1,000 feet or a mile or even 5 miles down that might, just might, contain oil? Astronomers are able to study the cosmos in many ways. Physicians, of course, can look inside the human body. And geophysicists have learned to decode the secrets of the Earth to depths greater than the length of Manhattan Island. There are no easy lakes of oil down there, no nice, neat reservoirs of energy. Oil, the remains of marine life that once lived in prehistoric seas, exist by the relentless geologic events of the past. The first phase of the geophysical search for oil is usually done with not one, but 2 or often 3 methods.
Okay, take it up.
The magnetometer attached to our plane measures the Earth's magnetic field. With it, geophysicists can gauge certain magnetic variations in the different types of rock. Oil is generally trapped in sedimentary rocks such as sandstone, softer, more porous rocks, less magnetic than the older rocks. Gravity tells us something else.
We've moved into this area that we think has potential for hydrocarbons. We're beginning a gravity and magnetic survey.
The sedimentary rocks are also lighter than the older rocks. They exert less gravitational pull. So the geophysicist looks for the presence of lighter structures, which register a lesser value on an instrument called a gravity meter, or gravimeter.
We'll read the instruments at this point, then we will survey new points throughout this area, and the gravity and magnetic values will be computed and posted on the map to form a contour map that we'll be able to relate to the geology and hopefully pick out some prospects for hydrocarbons.
By measuring gravity in different locations, the Earth scientist tries to support the clues given by the magnetometer. The third and most important method, the technique with which geophysicists have literally preserved the industrial capacity of this nation and the world, is seismic exploration. Dynamite to shake the Earth gently, just enough to set in motion subsonic sound waves that reflect, bounce off the different formations deep inside, and come echoing back.
Okay, Keith, get it hot on 2148. Here it comes.
These returning seismic waves, or reflections, are retrieved by small Earth microphones. They're called geophones, or just plain jugs, by insiders known as doodlebuggers.
We've just recorded the return echo from the seismic explosion on this digital cassette. The cassette is a single trace of the geophone pattern within the 200 foot near the box. The geophone generates an electrical impulse that is converted in this box to digital numbers, which can be read by a computer. We will take this data and composite it into a representation of the subsurface structure. These are representations of the geologic formations at a depth of 3.5 seconds, which equates to about 14,000 feet deep.
Porous rocks usually transmit sound more slowly than denser rocks, and the slower speed of the returning echoes might, just might, indicate the presence of sandstone or porous carbonate rocks.
Here it comes.
But the sandstone itself is no guarantee that oil is trapped inside.
It's been a good day. All the dynamite shot like it's supposed to. Had good swings, swinging the jugs and boxes. I have about 4.5 miles today. And what I enjoy doing is being able to see at the end of the month our production, looking at the plots of what we've shot, trying to determine if it is a good area. But you catalog it in your mind, so whenever you come back to an area, you know you're going to have good data. Here we're looking at station number, get the number of files, pull out your recorded tape, write down the box number, 332, station number, again 2249, and there are 28 tapes, 28 files on tape. This is line 48. That is recorded tape. Put in a blank tape. That clears your file count. Shut her up. Put her back in. Plug in your power cord for charging overnight. Say goodnight. There's the last three. Your final clear is 2174. You'll have a pull list for me in the morning? Okay. It looks good down about 8 seconds so far. Is it? Yeah. How's your golf game? Fair. Good. I'm going to go drink one. We'll see you. All right. Shot off the coast of Brazil, going into Belém. Stayed down there about a year and a half. There's a lot of stress and strain in this business, but I think that's what keeps most of us going. The divorce rate's pretty high in this business. I was lucky. I met my wife while I was doodle bugging. She's followed me all over the world. She maintains a home. I think that's what's kept us together in Houston. And the 2 children that have been in school, and they're fairly stable. They don't call me Uncle Daddy anymore because I do get home occasionally. 2152, here it comes.
What we're looking for with our sophisticated geophysics is, shall we say, the Empire State Building lying on its side under about 2 miles of a jumble of different kinds of rocks and different layers of earth above, and with a irregular surface on top of the earth, and all of which combine to produce a great deal of confusion on our data.
Without the geophysicists' knowledge of sound, without their mastery of its capacities and limitations, the majority of our greatest oil fields would remain undiscovered, and the world would have run out of gas at the pump years ago. To improve the sound, one might wish to record the opera singer from several spots. This to help eliminate noise and false echo. For much the same reason that the geophysicist wants to listen from different locations to seismic waves returning from a possible oil reservoir rock. It was that need to produce a clearer seismic record or picture of the subsurface which set Harry Main and others in search of a solution. Harry Main revolutionized the science of finding oil with a technique he named CMP, the Common Midpoint Method, or as it is often called today, CDP, the Common Depth Point.
Didn't expect that to be there. For many years, we did seismic work with only a single source and receiver position, so that each representation of an echo from a point on the subsurface or a reflection was only a single representation of that point. In the early 50s, I devised a new method whereby I used a series of pairs of sources and receivers, with all of which had a common midpoint, so that all of the echoes which were received from these different pairs were different positions or had a different aspect look at the subsurface. So I said, well, if I look at this thing from several different aspects, I might be able to keep the noise from duplicating. So by moving the source and the receiver in opposite directions about a common midpoint, I hope to get the noise to cancel itself out and get the reflections from this common midpoint to reinforce each other. Now, what we attempt to do is to follow a given formation within the Earth. This entire traverse may represent something like 5 or 6 miles.
What we're trying to do with our geophysical work is to learn how the Earth is built, how it is structured, how the various layers are laid one on top of the other, and how the various types of deformation occur in the Earth. Here's a chart that shows some of the different kinds of traps that we find. The simplest and most obvious of these traps is an anticline. The anticline is basically a hill in the Earth, capped with rock through which the fluids cannot flow. Stratigraphic traps, of which on-lap is one example, or trap pinch-out against an unconformity, are very common. This type of trap, the great East Texas oil field, is of this type of accumulation. We can see some of those over here on this other section here. For example, right in the area, right in through here, we have, you can see this layer of rock, of earth coming on through here, pinching out against this other layer coming on down through here to produce a trap of that type right there. And there are other places on here also where we can see similar types of oil traps. We have rocks that were formerly continuous and then have been broken along some plane and brought up into an offset position like this. And then the oil that might be present in the porous rock over here flows on up till it hits that fault plane and it cannot flow anymore, so it is trapped up there. And many of the world's biggest oil fields are of that type also. That's a very common type of trap. That's, in fact, probably the most common type of trap that we run into in our business.
The search for oil is a vast scientific and human puzzle that must be solved anew every time. A puzzle involving an intensive and costly effort and luck. A puzzle that is as different in Alberta, Canada, as it is in Saudi Arabia, as dissimilar in Kansas as it is in Egypt.
The vibroseismic is one of the newer energy sources for seismic exploration. And instead of using a strict sudden pulse such as it might be generated by a dynamite blast, it generates a long, continuous wave vibration. Dynamite is still unchallenged for those applications where we cannot get the heavier machinery involved. It was think out of the site in soft marsh and swamp terrain.
Vibrators operate around the world, gently forcing salvos of sound waves into the earth, gathering data in amounts up to 10 million bits per second, and using more magnetic tape than any industry in the world. On land in parts of the United States and Europe, the cost of a seismic survey runs from $1,500 to $25,000 a mile. But the world sometimes has to pay a lot more than that for its dependence on oil.
The fundamental reason, of course, up here was the fact that we really believed that this was a basin that would generate huge amounts of oil. We had all the elements for the trapping features, and we could pack a tremendous amount of oil into features the size of what we were looking at up here. Of course, at that time, we didn't know that Prudhoe Bay was up here. We didn't know that this thing could exist, especially with the magnitude of the structure that was eventually found.
Well, this is the probably one of the most critical maps ever made of Prudhoe Bay. It was made by Pete Clara with Richfield.
Yeah.
And I believe, if I'm not right, Harry, this was the map that Richfield based their bidding on the state lease sale in 1966, which determined the eventual ownership of Prudhoe Bay.
That's right. The industry had had 10 dry holes in a row up in this part of the world. We just finished drilling the Susie, 60 miles south. Union had drilled the Kukpuk over to the west. And here we were about to spend another approximately $5 million, which in those days was a fortune, even to an oil company, to drill another test. And the risk of drilling this well was probably something in the order of 1 in 1,000. We were the last company left to explore on the North Slope. Sinclair and BP had moved out. Union had drilled their dry hole. And when we drilled the Prudhoe Bay State #1, I'll never forget flying up there in the winter when it was dark and there wasn't another light to be seen until we spotted the rig lights up there at Prudhoe. Most of the companies had essentially the same kind of data. They'd acquired it in the same time frame. The interpretations, as we found out later at least, were basically the same. And the difference was, I guess, our aggressiveness and the conviction that we had a reasonable course to follow, and we were going to follow it to the end. And we hadn't finished by drilling the Susie well. We had to go north. We had to drill Prudhoe Bay, and we had bought the leases, taken a jump on the competition by having acquired a bigger lease position than anybody else. So really, the drilling at Prudhoe Bay was a culmination of all the ideas that had been building from 10 years before when we made our first entry up here with a field party in 1959. A lot of people have said that we were very lucky to find Prudhoe Bay, and I have disputed that for a long number of years because, as is true, we mounted a very solid, sound scientific effort up here with all the latest technology that we could apply, including the best seismic, and we afforded ourselves the opportunity for success to occur here. So we had some serendipity, but we weren't just downright lucky in this thing.
In 1937, Sidney Kaufman, then a party chief for a Shell seismic crew assigned to map a structure in South Texas, directed a daring and unorthodox field operation. Without the knowledge or approval of his superiors, he carried out the first seismic reflection survey of the sea floor on the bottom of the Gulf of Mexico. 4 miles in length, instrumented with a single geophone for each of 8 channels, surveyed by shore-based transit, and shot by sinking cases of dynamite. That marine seismic survey ushered in a new era of exploration offshore and vastly increased the role of the geophysicist because geophysical techniques alone provide the ability to see beneath the ocean.
In the early days in the southern North Sea, some of the work was through the minefields of the Second World War. That was tricky. The war was important in the development of geophysics, in instrumentation, in positioning, navigation systems in particular. But I suppose the most important feature was in the men. Men were available who knew how to live rough, who could even enjoy it, and who could get the job done. The North Sea was a very satisfying place for a geophysicist to work. The Earth responded and gave up her secrets. Almost any good idea you had, you'd try it, and the results would improve. Take reverberation. Now you let off a bang in the water, and the bang rattles up and down between the sea surface and the sea floor, and the sound goes brr, brr. And all the echoes coming back, they all go brr. So the sound becomes jumbled and confused. the same effect in a church. Why do you think church music is traditionally slow and long drawn out? What was the reason for the ancient plainsong chants and the slow intoned responses? Same problem, reverberation. Sound rattles back and forth between the hard, bare walls of the church, and the sound becomes all jumbled and confused. You can hear the reverberation. So, if you want to hear the message clearly, you need to remove the effect of that reverberation. If someone were irreverent enough to sing a Gilbert and Sullivan patter song in a cathedral, you would not be able to make out the words. And the early seismic results from the North Sea, they were just as garbled. But the geophysicists found the solution. He was able to remove the reverberation and see the deep rock layers below.
Much as sound filters remove static from a radio broadcast, computers can filter unwanted echoes and noise from seismic data.
Aberdeen, Scotland. A port. A country rebuilt by science.
Hoist the signals.
The world's geophysical navy consists of 134 vessels. One of its flagships, on duty these days in the North Sea. And the CECIL H. Green, now searching the Gulf of Mexico. One of the largest and most advanced seismic ships afloat, the Green costs $500,000 a month to maintain.
Western wind, Cecil H. Green.
In these ships, with these men, we can trace the future of oil and gas exploration. More than 5 out of every 10 barrels will be found offshore. It looks deep beneath the ocean floor as if it had eyes. It has, in fact, the most discriminating ears in the world. Its thousands of hydrophones inside a streamer cable respond to reflected seismic waves generated by air guns blasting the seabed and the rock formations below with wave upon wave of sound. As it happens on land, the echoes are picked up by the hydrophones. The data are translated into electrical digital signals and recorded on magnetic tape. As much as 10 million bits a second, as many as several hundred boxes of tape. Facts, all of them. Facts about the subsurface. Facts to reveal nature's best-kept secret.
Our job, like I said before, is to, first, the safety of the vessel. And then secondly, the safety of all the people on board. Now, third, our primary job is to serve the seismic interest on there, because after all, that's the only reason we're out here for, is for them. When they begin their operation back there, we have to go down a straight line. So we have this machine here. It is the output of a computer down there that tells exactly where we are within feet, and it gets its information from 2 different survey systems ashore that transmit out to us. A system on board that transmits to these shore stations.